Okay, so let me just summarize what we did yesterday. So yesterday we were discussing the general definition of stochastic processes. Uh, General definition of stochastic processes, and then we said what a Markov process, which is a special class of stochastic processes. So Markov processes are those which have like one-step memory. Uh, and then we discussed about like some properties of Markov processes, which are basically uh, that it satisfies this Chapman-Kolmogorov equation. Okay, so Markov process is basically something which satisfies this, that if I ask what is xn given and then this is just equal to p. Okay, so I just need information about the last time. Okay, so this is time is ordered. Okay, so t1 and so this is a definition of a Markov process. And so so we'll also come discuss some examples of systems which are non-Markovian. But we'll see that quite often you can actually turn a non-Markovian process into a Markovian process, okay, by just introducing extra variables. Okay, so I think Sanjib mentioned something like if you have equation like d2x by dt square equal to eta, so d2x by dt square equal to eta. So this is non-Markovian. Okay, if you think of x as your variable, and so this is a stochastic process, x as a function of time, right? This is non-Markovian. Why? Huh? Yeah, so if you want to find xt plus dt, if you just know xt, it's not enough. You need xt and vt. Right? So you can make it Markovian immediately by just defining dx dt equal to v and dv dt equal to eta. So now I have two variables. So it's a two-variable stochastic process. And so this is y. And now this process is Markovian, right? Okay, so then we define the Chapman-Kolmogorov equation. Chapman which basically says that P of, let's say, y3, t3 given y1, t1 is equal to t1. Okay, and again here t3 is greater than t. Okay, so here t2 is not integrated over, just this variable y2 is integrated over, and then you just get this, okay. And then we discussed homogeneous processes. So chain basically means both y and t are discrete variables, so they can take discrete set of values. And in that case, basically the process is, so this becomes p y3, let's say, okay. Homogeneous means it's just depends on the time difference. Okay, so and then we used a different notation. We called this as equal to W. Okay. So T is better maybe. Okay, so let's call it T. So T, probability of transition from state Y1 to, no, so T we use if, so this is for any time, but if we set this as 1, so that special thing, Y2, 1 to Y1. So just the transition probability in one step, right? So that we call the, let's call it T now. T, Y2, Y1. So probability of transition from Y1 to Y2. Okay. We also, instead of, so then we said we'll just call it Tij. So this is transition from J to I state. Okay, and with this notation, then the time evolution of the, so we basically we have some configuration space. So these are different configurations that the system can take part. So we said let's there be 1, 2, 3, total number of configurations is m. So the system is basically doing a random walk in this m-dimensional configurational space, right? So actually, I mean, any Markov process, I mean, finally it's basically a random walk in a, I mean, in some configuration space. So basically, it's you start from somewhere. It has some probability of going to various places, and that's given by this transition matrix. Okay, and then you want to see. So at each point, you have some probability associated. So P1, P2. What's the probability that the system is in this state? What's the probability it's in this state, and so on. So you can construct a probability vector. Which I call P. And then the way this probability vector evolves in time is just through this equation that P n plus 1 is equal to T P n. Right, and so in component, maybe I'll put so in component form, this is just Pi n plus 1 time is equal to Tij Pj. And of course, summation over j. Okay, so this is, I hope it's clear. Any questions? Okay, so yesterday there were some questions. So one question was, is this a necessary? So this, of course, it's a necessary condition for a process to be Markovian, right? Because we have shown that any Markovian process will necessarily satisfy this condition. Okay. But is it also a sufficient condition? So supposing I find some process which satisfies this equation, and then is it obvious? Is it automatically a Markov process? So the answer is no. Okay, so so actually there's an example in this book by Van Kampen. So actually a very good place to read all about this is Van Kampen. I think that's probably the best book on stochastic processes. Okay, so there's an example in Van Kampen where there's a process which basically there's a single variable which can be either 0 or 1. Okay. And then supposing I just give the probability, so stochastic process means I have to, so this variable x is there, it can take values 0 and 1, right? So its configuration space is just two-dimensional configurations. There's just two configurations, 0 or 1. And then stochastic process means I have to give probabilities of all possible sequences, right? So supposing I just look at some 3 sequence, so 3 time instants, and I give the probabilities of all the possibilities. So in 3 time instants, there are 3 possibilities. Okay, so 1, 0, 0, I mean there are 8 possibilities. 1, 0, 0, 0, 1, 0, 1. And then there are 4 other possibilities here, right? So this is time. Okay, so it starts from 1 and goes to 0, 0. So then if it's a stochastic process, you have to give, say what is the probability of this sequence, what is the probability of this sequence, what is the probability of this sequence, and what's the probability of this sequence, right? Okay, so this is time 1, 2, 3. Okay, time. Okay, so now supposing I specify the process by saying that this process occurs with probability 1/4, this is 1/4, this is 1/4, and this is 1/4. right? And all the other processes don't occur. Okay, so I don't allow the other processes; they occur with probability 0. Okay, so now now it's easy to check that actually given this rule for the stochastic process, I mean this condition is satisfied. Okay, so I mean you can just check, for example. So what is so supposing so what does it mean for this rule to be satisfied? So I choose my times. Let's say t3 is 3 and t1 is 1, right? And I ask for various transition probabilities. So let's say p y at time 3 given y prime at time 0, not 0, let's say 1. So there are 3 different times, right? So this rule has to be satisfied for all times and all y's. Right? Okay, so now supposing I check whether this is, given this, whether this is satisfied or not. Okay, so first of all, this is not, obviously this is not a Markov process, okay, because if I just tell you the transition between this, then I'm giving transitions, I mean, this depends not just on the previous step, but also on the earlier step, okay, so it's a two-step process. So it's obviously not Markovian. Which one? This one? So because I'm saying that this at third time, the outcome depends not just on this, but also on this. Okay, so let's supposing we can compute this transition probabilities. Okay, what's the probability of transition from let's say okay, so let's just take two particular values. So what we want to check. See, I mean, given any stochastic process, it won't be Markovian, right? I mean, it will be Markovian only if I say that it has been generated by this, yeah. X can take 0 or 1, right? Now it's a process in time. So in the first time, it's, let's say, started with 1. In the next time instant, it's 0. Next time, it's again 0. Okay, so this is a particular realization of the stochastic process. And I'm specifying that this process occurs with probability 1/4. No, what?
Why you can't take a value 1
at t equal to? This one? No, see, I can specify whatever I want, right? I mean, I give given a stochastic process, I mean, I just have to, what did I define the stochastic process? That basically I have to give all these probability distributions, right? So if I am looking at time three-step process, if I tell you the full distribution, that's complete specification of the stochastic process. Okay, so what was the definition? Okay, so basically here I've given this x1, x, yeah, x1, t1. Okay, so for this particular process, I have specified this distribution. Okay, so now what we want to check, if it's Markovian, it should be that this is given by, okay, so this is of course, okay, if it was Markovian, it would have been P of x1, t1. Right? I mean, it should have been given by this. Okay. So now, okay. So first, let's compute these objects. Okay. So given this full distribution, of course, I can always compute this conditional probabilities, right? Because this guy has information on the full things. Okay. So now, if I want to compute this, okay. So. Okay, so if it's Markovian, it would have satisfied P of y3 given x is like a 0 or 1, right? Yeah. So it can each time it can take two possible values. So there are. Huh. How? No, what do you mean by how? See, I mean. Okay, what is it? See, if I'm tossing a coin, right? So then, of course, each time I'm tossing coin, 0 and 1 are equally probable. But this is not tossing a coin. This tossing a coin is like I mean, it just depends on. I mean, the present time. It doesn't even depend on the previous time. No. See, these are the successive steps. No, they're not exclusive. Yeah, they're not independent events. They're not like a coin toss. It's independent events, right? If 0 or 1 first step, next step, it's completely independent of what I got in the previous outcome, right? So if it was a coin toss, then what are the possibilities? I mean, 1 0, okay, 0 0 0, 0 0 1 1 0, and all of them have probability 1/8, right? So that's a coin toss. Right, yeah, exactly.
So if you had a Markov process, then you could get 0 0 0, which you cannot get here.
Exactly, right, yeah. So because I'm saying 0 0 0, I mean if 0 0 here is allowed, right? So if it was a Markov process, I mean 0 0 0 would have been definitely allowed. Right, yeah, no. Even if it's Markovian, I mean, yeah, actually that's true. I mean, all the possible combinations would have been, I mean, depends on your Markov process. Supposing I say that if it's a Markov process where 0 to 1 is allowed, but 0 to 0 is not allowed, right? That's, I can have such a Markov process. Then of course all the sequences still won't come, but I will still have some, yeah. But here 0 to 0 is certainly allowed, but therefore 0 0 0 should have been allowed. Third result? Where here? Yeah, if it's 1 0, it has to be 0. Right, yeah. And not has, yeah, out here it has to be 0 because these are the only possibilities. I mean, you can't have 1 0 1, definitely, yeah. Okay, so it's clear that it's non-Markovian, and then you can also check that, in fact, this thing is satisfied. Okay. So I'll just do one example because actually it's good to this gives you a good understanding of probability. Okay. So if I just try to compute p of 1 3 given let's say what 0 1. Okay, so what is this? Given it's 0 at time 1 step, what is it? What's the probability that it's 1 at time step 3? Given this is my process, huh? Is it 1? Given it's no, given it's 0 half, right? Because there are only two possibilities, and it has to be it's 0 to 1 and 0 to 0, both are half. So this is half. Okay, and in fact you can convince yourself that all of these are halves. Okay, so therefore I mean here there are two possibilities: half into half plus half into half. So that's 1/4 plus 1/4. That's again half. Okay, so therefore this Chapman-Kolmogorov condition is satisfied by this process, but it's non-Markovian. Okay, so it's not a necessary and sufficient condition. There's a right eigenvector with eigenvalue 1, which I call which is the ground state. And there's a left eigenvector which we constructed yesterday, which has also eigenvalue 1. Right? And this state was very easy. This state chi0 is just a vector with all elements 1. Right? So because of this property that, so this follows from Okay. So, okay, so now the next thing you can see is, supposing I look at the other eigenvectors of T, then I mean I can always make them orthogonal, right? Left hand eigenvectors can be chosen to be orthonormal, which means that chi of 0 times phi of n for n not equal to 0 is equal to 0, right? Now this element has all vectors, all elements 1. So therefore this means that all eigenvectors will have some element which are negative, right? Otherwise it can't be 0. Okay, so let's just give, just to have ideas clear, let's just give some examples of this T matrix, okay? So I'll just give two examples. One is if you have a random walk on a lattice, so let's say L sides. So here I have a single walker, let's say start with, and so then so the value of m, so the position of the walker is basically my stochastic variable. So that's so y is basically the position of the walker, and so it can take L possible values. So m, the configuration space m is just L dimensional. Okay, so now what is this T matrix in this case? So the rule is that let's say I can go from 1 to 2 with probability p, and from this to this with probability q. Okay, so I can move to the right with probability p and left with probability q. Okay, so earlier we wrote, of course, this equation that p of x and okay, so let's also put a probability that the particle sits at a point with probability 1 minus p minus q. Okay, so with probability 1 minus p minus q, the particle just sits at the origin, sits at whatever place it starts with, okay. So then I have to add one more term. So what should I add? Plus 1 minus p minus q, probability it's at x at n. Okay, so now how do we write this matrix T for this equation? So this is I mean, I've written is a difference equation, but basically now since this is a linear equation, I can write it in matrix form, right? So then if I just call it P1, P2, like that, PL, then what is this matrix? This matrix is basically the diagonal elements are 1 minus P minus Q. Then this one is what? P1 minus P2, Q. And if it's a ring, the last element is P. Right? Then you have P1 minus P minus Q. Okay, and so on till the last element, which is Q. Okay, so this is the this is time n plus 1, and then you'll have the same vector at time n. Okay, so this is the T matrix for this. I mean, so it's the same system, but I can write it in this matrix form. Okay, and you can check that this column sums all are 1. Okay, so now, okay, so this is one example. The other example is, again, let's look at a spin system. Okay, so if you have a single spin in a magnetic field, its energy is given by e to the power minus hs. Okay, and then what? Okay, so let's say h is greater than 0. So basically here my the stochastic variable is the spin, and it can take only two values, right? +1 and -1. So y equal to s equal to plus minus 1. Okay, so now if I have such a spin, I mean, of course, it's a classical thing. So just like that, it has no dynamics. And but what we do, I mean, so many of you have done this simulations. Like, how do you equilibrate a spin system? Okay, so there's this thing called Metropolis algorithm, which is a Markovian dynamics basically. Which tells you how the spin evolves in time. Okay, and the rule is, so Markovian means basically you have to give the transition probabilities, and the probabilities in this case are basically that t Okay, so let me just explain what this is the probability that given it's in S, that the next step is actually flips. Okay, so the probability, I mean, so what you do is, so what you want finally is that you choose the dynamics in such a way that the steady state that I've been talking about at long times, this one should actually be the equilibrium distribution. Okay, so that's the basic logic, I mean, that what you want. And the way to choose this matrix which ensures that it will at long times go to equilibrium is to have some rule like this. Okay, so this rule says that when you flip the spin, so its energy changes, right? Its energy goes from some Es to E of minus S. Okay, so this is E of S. So it goes from it, and so this is the change in energy. So if the change in energy is less than 0, so which means that if energy goes down, right? So then this factor is so then you always flip the spin if the energy goes down. Okay, so you try and if it increases the energy, then then the transition probability is e to the power minus beta change in energy. Okay, so that you can just write it in a compact way like this. So the rule is, if you so any transition which lowers the energy, you flip it with rate epsilon. If it increases the energy, you flip it with rate epsilon, with probability epsilon into e to the power minus beta delta E. Right? I hope that's clear. Okay. So now you can write down what this T matrix. So here the configuration was 1 to n, and here it's just 1 and minus 1, and 1 and minus 1. These are the allowed configurations. So what is the probability of transition from 1 to minus 1? So spin is so this spin up is lower energy, right? So if you flip from 1 to minus 1, the energy increases, right? So therefore the probability should be epsilon times e to the power minus 2 beta h, right? And from minus 1 to 1, 1, but I have a factor epsilon, right? So I'm putting a factor epsilon for some reason. Epsilon, and what is this? This sum has to be 1, right? So it has to be 1 minus this. Okay, so this is the T matrix in this case. And you can actually easily verify that if you put e to the power minus beta h, what will you get? If I what will I get? Same thing, right? So you can, I think you can just do this easily. This into first you get e to the power minus beta h. So it's a steady state eigen. In this case, what is the steady state? Yeah. So here also you can easily check that the steady state is a vector with all 1 by L, right? Because if you are moving on the ring, I mean, after some time you will visit all sides with equal probability, right? So it's a uniform distribution. Okay. So. PI steady state. So if it's a steady state vector, I mean, if it has reached steady state, then it whatever this probability vector should satisfy this equation. Okay. So now there's a I mean, you can choose your supposing you want your system to reach some desired steady state. Okay. So then there's a particular way to choose the transition rules so that you always reach the required steady state. Okay, which is what we did in this Metropolis algorithm. So it quite, I mean, in this all the simulations, what we want is that the steady state should be the equilibrium state, right? It should, the system should reach equilibrium. Okay. So in that case, what you do is, I mean, so one way of ensuring that the this, I think Shushanta also talked about this, equilibrium state. Okay, so now if you choose the rate such that this is satisfied, then you can easily show that actually this is the equilibrium state. Okay, so how do you show that? I mean, from this, is it obvious that I mean, I mean, supposing I have chosen my Tij's such that they satisfy this equation. Okay, so now I want to show that Pj equilibrium is actually a steady state. So I have to show that this is equal to Pj. It doesn't change, right? So this is okay. So I should mention this is for this is no summation over j. Sorry, I should say that no summation. So it's valid for every possible pairs that you can choose. Okay. So now we have to, okay, so here of course there's a summation. Okay, so now given this, I mean, you can actually show this, which is quite straightforward. So basically you take Tij, Pj equilibrium and sum over j. Right? So now because of detailed balance, this means that Tji P I equilibrium, and you still have a summation over j. Right now, Pi comes out and this is 1, right? So Pi is you sum over j, and this because of the rule of the T matrix, this is 1. So this is equal to Pi equilibrium. Okay, so therefore that's the idea. Okay, so here when we chose these rules, we made sure that this is satisfied. Okay, that's why the system automatically reaches thermal equilibrium. Okay, so so we wrote pi n plus 1 equal to okay, so now what I want to assume is that this transition rates, for example, this quantity is out here, these transition rates are of order delta t. Okay, so that's why I put an epsilon here. Okay, so because if I want to go to the continuous time rate, then the probabilities should depend on my time step. Okay, so it's like when you went from random walk to the diffusion equation, you introduce some time scale, right? So so therefore I mean we'll assume that all these matrix elements of diagonal ones are all order delta t. Okay, so now and then I'll take the limit delta t going to 0. Okay, so okay, and the diagonals are not order delta t, okay, because the diagonal, I mean, we know that the total sum is 1, right? So then this can't also be order delta t, right? So this has to be 1 minus something which is order delta t. So all the diagonals are 1 minus order delta t. Okay, so now what we do is, if you want to go to the continuous time limit, basically we take pi n plus 1 minus pi n is equal to n, right? So I've just, so pin I've written as delta ij times pj. Okay, and then we divide by time. So now we assume, so we'll, okay, so let's divide by delta t. And so here now we call time is equal to n delta t. So that's our time variable. And then this just becomes del pi del t. So del pi by del t. And this object that I'll get, this I call wij. Okay, so this is summation j. So now it's del p del t equal to w of p. Where so wij okay, so now one thing you notice is that, and this is delta t going to 0. Okay, so one thing you notice is that wij, if you sum over I, that's now what? Sum over I is 1 minus one minus, huh? 1, right? 1 minus 1. So that's 0. Okay. So in this representation, if you sum the column, it's 0 now, right? Okay. So let's just write this. I mean, so here, if you do what we have done here, so what will you get? So corresponding to this process, W will become. So we have to subtract this unit matrix, right? So all the ones out here will go. You'll just be left with minus epsilon, 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 and minus epsilon, and then you divide by delta t, right? So okay, so then epsilon by delta t, you call it some rate, right? So earlier these were transition probabilities. Now these are rates. So these are dimension of 1 by time. Right? So it's epsilon by delta t. and so it's called epsilon by delta t as some rate r. So then this becomes minus r e to the power minus 2 beta h, and this is r, and this is e to the power minus 2 beta h, and this is r. Okay, so you can see that the sum of the columns is now 0, right? And of course this will still continue to be true. And here if I do the same thing, so the ones on the diagonals will all go away. So all these ones go away. And okay, so now so I called P by delta T. So this is, earlier it was probability, now it's a rate, and I call it, let's say, R1, and Q by delta T is equal to R2. Okay, so then this matrix basically becomes minus and so on. Okay. Okay, so now in this case also you'll get a steady state, and in this case what is the steady state will satisfy, I mean, so steady state now means del P del T equal to 0, right? So therefore it will satisfy WP steady state equal to 0. Okay, so it's the, now the, it's the 0 eigenvector of this matrix. Okay, so by the way, this is what is usually called the master equation. Okay, so this is in some sense it's just the continuum limit of the this discrete Markov process. So this is called the master equation. Okay, so now let's see how you solve this equation. Okay, so to solve, basically the simplest way is to just find the eigenvectors of this. So if you find W, let's say if I find the left and right eigenvectors, so phi alpha is equal to some lambda. Okay, so the lowest eigenvector, which is just the ground state, I'll call it alpha phi 0. So that is just 0 phi 0. And all the other eigenvectors, what again you can show using this Frobenius theorem, that all the other lambda alphas, so the real part of lambda alpha is greater than 0. Okay, so then what you do is, and you can also find the left eigenvectors. So let's, okay, let's. Okay, no, okay, it's just, you'll see why I wrote it like, I mean, I could have written lambda alpha, then I would have said it's less than 0, right? I mean, I can write it either minus or plus. I'm just putting this condition that the real lambda alpha is greater than 0. Okay, so now how do you solve this equation? So basically you'll expand P as and so this since this is I mean this eigenvector form a complete set, you can always expand any probability vector in terms of these eigenvectors, and then just plug it in this equation, and what you'll get is sum over C alpha dot is equal to WP. What WP is, so the, okay, so what is WP is, Okay, so now you want to extract C alpha dot. This is right here. Huh? Okay, so now you want to get an equation for C alpha t. So you have to take a product with some chi alpha. Okay, so let's take chi beta, where chi beta are the left eigenvectors. So the important thing is that this W is typically not a symmetric matrix. So it will have different left and right eigenvectors. Okay, so W, so these are the left eigenvectors. Beta. Yeah. No, that is always true. I mean, if you have like at least if you have a finite matrix, and if you find all the eigenvectors, right, they will form a basis. That's irrespective of whether it's Hermitian or not.
No, no. If it is not symmetric, you can guarantee that
Basis is?
basis is complete.
No, but you can always like if you unless you have this like degenerate this condition of degenerate eigenvector.
Quoting from detail that book, there it mentions that if it is not symmetric,
Huh.
it's documented, it's not always guaranteed that the basis will be complete.
No, this is true definitely. You're quoting from?
Detail, there is no.
Okay, I don't know what what exactly the statement is, but this one definitely forms a complete set. Okay, I don't know. Okay, let's see if there's a simple argument. W. Jayant, do you know any simple argument why it should be? If I have a complete. Okay, so let's assume it's a complete set, which is, I think, usually true. Okay, so now you find the left and right eigenvectors and take a product, and so you get C beta dot is equal to minus lambda beta C beta. So therefore, C beta t is equal to the power minus lambda beta t C beta. Is equal to. Okay, so let's write the first state separately. Or okay, so right now let's write size. C beta C alpha 0. I guess it's okay, right? Yeah. Okay, so now we still need this phi C alpha zeros, and that we can just take t equal to 0. So therefore, if we put t equal to 0, we know the state at time 0, and so this is not there. So and we take a dot product chi alpha is equal to C alpha 0. Right. So this is clear. Okay, so therefore P of t mission Okay, so this one I've just broken it up into alpha equal to 0, which is supposed to be the steady state, and alpha not equal to 0, right? Okay, so now here, okay, so here actually finally we know that it should just go to 5 zeros. So this term actually should be 1, right? So that actually you can easily show that this is 1. Can people see why it's 1? Chi0, P0. So chi0 is the left eigenvector corresponding to the steady state. Yeah, why is it 1? Because we said that chi0 is what? Chi0 is the left eigenvector with 0 eigenvalue. No, so what was chi0? The left eigenvectors, the steady state left eigenvector was 1, 1, 1, 1, 1, right? So this is 1, 1, 1, and this is the initial probability vector, right? So which is P1, P2, P2, and sum of that is 1, right? Because it's normalized. So therefore this is 1. Okay, so therefore now what you see is that we also said that the real parts of all these lambda alphas are greater than 0. So therefore at long times, t infinity, all these terms will go to 0, and this is you just go to reach the steady state. Okay, so, so then of course the other question that one is interested in, how does it approach the steady state? And for that, at long times, the smallest eigen value will dominate. Okay. So you just, if you order all the eigenvalues like lambda 0, so this is real parts. And so on, real. Right. So then, so lambda 1 determines relaxation to equilibrium. Okay, so therefore quite often the lot of effort is just to find this, so given any stochastic process, you know this W matrix, and you want to find its ground state, which is just the steady state, which need not be equilibrium, right? So if it's a non-equilibrium process, the steady state won't be equilibrium. And then you also, if you're interested in how it approaches the steady state, then you also need to find the, the first eigen value. Okay, so the relaxation time is basically tau is given by 1 by lambda 1. Okay, so this is some lattice, and you have 1, 2, 3, 4, 5 L sides, and then you put n particles on it, right? Okay, so size L. Okay, so and the so each of the particles, what they do is, if there's an empty, if the sides next to them are empty, then they just move with whatever rate. Like if so, we already looked at this problem where there was L sides and just one walker. So 1 to L, and there was one walker. And we said that the rates, it moves with rate R1 to this side and rate R2 to this side. So, so if these walkers are still doing that, but if there's a nearest neighbor which is occupied, then it can't move. Okay, so that's the only rule. Okay, so given this, of course, now it's easy to write down what the W matrix is, right? So the basic, so we'll just do some simple example and try to write this W matrix for let's say 2 particles and so on, and then make some. So then you'll hear about this again more in next week. Okay, so okay, so first let's again recall how we solved this problem, right? So what did we do? We wrote a equation like if it's dp I so with rate R1 it can come from px minus 1 or yeah, so px minus 1 minus 1, and with rate R2 it comes from px plus 1. So then what is the other? This is the gain terms, right? Now it's a rate equation. Okay, so this is not a probability things, it's just rates. So, and then minus, so this is just the loss term, E of x. Right? So now time is continuous, okay. So, okay, so let's see how would you solve this equation first of all. So given what we have, so how if I want to, given it starts from some point, I want to find out how it evolves in time. So how do I solve this? Huh? Write a master equation. Yeah, I've already written the master equation, and you know the matrix also. Yeah, find the eigenvectors. Okay, so what are the eigenvectors of this matrix that I wrote? And this is a simple matrix, right? You should all know the eigenvalues of vectors of this matrix. Huh? Who said you said something? What? What? Of the there was I wrote some W matrix corresponding to this, right? That matrix was just this. I mean, there was some. I mean, it's the same thing. Minus R1 plus R2. And then this was, I think, R2 and R1. Some matrix like this. Huh? One is 0 and eigenvector is also 1, 1, 1, 1, 1, 1 or 1 by L, whatever. Right, do we know any other? I mean, this is a right? It's a cyclic matrix. It's a periodic matrix. Right, exactly. If you know tide binding, you also know this. Actually, whatever I've been doing, it's almost exactly like tide binding so far. I mean, right, yeah, and eigenvectors are easier than the eigenvalues. Yeah, actually it's just, I mean, see, once you have periodicity, then basically Fourier transform, right? So it's either IQX. So if you put, I mean, so the with, I mean, you can either write it in this form. So phi x is just e to the power IQX. Okay, and you can also think of them as vectors, right? And Q. So I can either write it just in component form or in vector form, right? But it's the same thing. So the components of the vectors are phi x is e to the IQX, and Q can take values. So it's a periodic lattice, so Q can take values. I mean, it has to satisfy some boundary condition, and therefore Q can take values 2n pi by L. Okay, so right. So if you so now and n goes from 1 to L, right? So now if you just change the value of n, you get L different eigen functions, right? We want L, there should be L independent eigen functions. So these are the L different eigen functions, and I mean, you could have started from 0 and gone up to L minus 1, which is maybe better. 0 to L minus 1, that doesn't matter, right? Because it's all periodic. So if you start from 0, the 0th one is just the steady state eigenvector, right? So 0, 0, 0, 1, 1, 1, 1, that's the steady state eigenvector. And all the other are the higher states. Okay, so here, these are the eigenvectors. And now if you just look at this equation, so we want, okay, so we have some W of phi equals to minus lambda phi. This is what we wanted to solve, right? And W of phi basically means this. So it's like R1 phi of x minus 1 plus R2 phi of x plus 1 minus R1 plus R2 phi of x is equal to minus lambda phi of x. Okay, and if you plug in phi x equal to e to the power iqx, so you get R1 e to the power minus iq plus R2 e to the power iq minus 2 minus lambda. So this is the qth eigenvalue, and so lambda q is okay, so if R1 was equal to R2, then you get what you get in the tight binding Hamiltonian, right? Because there it was symmetric matrix. So then you get real eigen values. But now because it's not a symmetric matrix, therefore you get complex eigenvalues. But the eigenvectors are still the same. Okay, so it's still the same set of eigenvectors, which are this. Okay, so now you have got your eigenvalues. So you can see that what is lambda 0? Lambda 0 should be 0. That's okay. So that's fine. And lambda 1 is something. Okay, so so we know all the eigenvalues and the eigenvectors. So okay, so in particular, if you want lambda 1, which we said was the first eigenvalue is kind of important. So let's also write lambda 1. So lambda 1 is R1, 1 minus e to the power. So now you just put q equal. Okay, so let's write the cos q. Okay, so to find the first eigenvalue, you have to put q equal to 2n pi by l and n equal to 1, right? So if it's okay, so the real part of lambda 1 is given by this, and this you can see is greater than 0, right? And so if L is kind of large, then this goes as actually 1 by L square, right? So lambda 1 is equal to R1 plus R2 minus, okay. Okay, so the real part of this basically gives you the relaxation time. Okay, so if you have a large lattice, one thing you can immediately see is that this goes as like R1 plus R2 by L square, right? Okay, so 4 pi square by L square, lambda 1, and so the relaxation time tau will be L square by R1 plus R2. Okay, so does this make sense? I mean that the relaxation time is L square by the rate. Huh? Right, yeah, exactly. So basically what should be the relaxation time? You have a box of size L and there's a diffusing particle, right? Relaxation time means how much time it takes to sample the whole thing, right? And because it's diffusing, the diffusion time scale is L square by the rate, right? So therefore this, we can see that it sort of makes sense. Sorry? So there's an oscillation also actually. So if you look at how it goes to the steady state, so now you have your complete this set of eigenstates, and you can expand the initial like the state and like write the complete solution like this, right? And then if you look at, if you just plot it, for example, if using just the first eigen value, what you will see is that so supposing I plot the probability that it's at some site like, so let's say it starts from some site like this. Okay, so initially this probability vector is 1 at this and 0 everywhere, right? And then I'm seeing as a function of time, how does the probability, let's say at this point evolve. Okay, so let's say p of some point x as a function of time. So initially it's 0, and then it will eventually go to it will exponentially go to this steady state value, which is 1 by L. Okay, so this is true if R1 is equal to R2. Okay, but for R1 not equal to R2, for the asymmetric case, so the steady state actually 1 by L, it's the same whether it's asymmetric or symmetric, right? Because in both cases, it will just keep, you'll have uniform density. But the steady states are completely different. One carries a current and the other has 0 current. Okay, and so so this is for R1 equal to R2. For R1 not equal to R2, if you plot how it goes to the steady state, it will be, so there's this oscillations. Okay, so the steady state value is still 1 by L. Function of time. So it will go like this, and then okay, so that's what we will get if you just plot that function. Okay, so okay, so now let's just go quickly to the n particle case. So how do you okay, so first of all, how do you write the master equation? Okay, so in this case, so first of all, you have to specify the configuration space, right? So we have n particles on lattice L. So how many configurations are there? Allowed configuration. So here there were only L allowed configurations, right? So now in this case, what is the number of allowed configurations? LCN, right? Yeah. So LCN. So that's the number of allowed configurations. Okay, and so now basically now my probability vector is this dimensional, and I have to write some matrix in this space. Okay, so the so first I have to specify the microstates. So in this case, so the best way to specify the, and one way you can do various ways. So each microstate is specified by N1, N2, N. Okay, so you just where Ni can be 0 or 1, right? So on each site, if there's a particle, you put 1, and if there's no particle, there's 0, right? So if you give this L numbers, then the state is completely specified, right? And the other way you could do is, if you have n particles, you could just specify the positions of the particles, x1, x2 to xn. So that would be another way of specifying, right? But I mean, let's do this. Okay, so now let's just do some examples. So let's say L equal to 4 and n equal to 2. So number of configurations is equal to 6, like 4C2, so that's 6. Okay, so what are the possible states? So the states are 1, 1, 0, 0, and let's see, it's on a ring, right? So 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, then 0, 1, 1, 0, 0, 1, 0, 0. Okay, so now let's try to write these equations. Del P 1, 1, 0, 0. Okay, so if I want to find the rate at which this state if, changes, the probability of this state changes, so it will get contributions from which states? So what are the terms that I should have? So it can, okay, so this state can come from, right, it can come from here because this particle could have from, right, it can come from here because this particle could have hopped here. It can't come from this state, right? So this state it can come from, this one no, this one no, this one yes, yeah, because this way I can just come here, and this guy no. Right, so there are only two states. So so what is the so you have to write some gain terms. So from this, what is the rate? This is so it is going like this, right? So that's R2. So this is just R2 times P of 10. Okay, and then this one is it's going to the right. So that's R1. So plus R1 P and then loss term is so it's gaining from this means it can also lose to those guys, right? So and the loss will just be minus plus R2 what is this? No, it's losing from itself, right? So it says P1100. So loss is always from that state. See, in this W matrix, all the off-diagonal elements are positive. Only the diagonal elements are negative, right? And this is coming from the diagonal element. Okay, so similarly, we can write another. Let's just write another one. P. Okay, so if you look at 0, 1, 1010, so that is this one. So it can come from, of course, this one. It can come. No, this one it can't come from. This one, yes, right. And this one, no. This one, yes. Okay, so this one can come from three possible states. Okay, so this is, okay, so we want this, so this is, No, third one also, is it? Okay. Okay, so there are four states it can come from. Yeah, so that's just what, so the first one is R1. Second one is minus plus R2. And then plus R2. Okay, and then you just have to add all this and subtract. So that's minus R2, R1 plus R2, P of the same thing, 1010. One zero zero 1010, some sequence like this. It can come from states which differ from this only by one move, right? So in all these cases, you'll see that it's just one move different. So it's not coming from states which differ very far, okay? So it's, just some one particle displaced states. Okay, so this equation, of course, now again you'll try to do the same trick. And so you have this W matrix. Okay, so what so that is more difficult to solve, of course. So one thing that is kind of interesting to note is that if you look at the symmetric case, okay, So in the symmetric case, if you look at this W form structure of the W matrix, the structure is exactly the same as the so there's this spin Hamiltonian called the Heisenberg spin chain. So this is a symmetric exclusion process. It's a symmetric Hamiltonian, right? And there's a Heisenberg spin chain, which is just which again you have heard in the previous lecture, which is given by minus sigma I z plus sigma I x sigma I plus 1 x. Okay, so this is the Heisenberg spin chain. You can write it in a slightly more nicer way, which is like sigma I z sigma I plus 1 z plus. So these are all polyspin matrices sitting on each side of a A, right? Okay, so now this thing you can write in terms of sigma I plus sigma I minus. Okay, so if you do that, then what you'll get is something like sigma I plus 1 minus plus I think maybe there's a factor of this factor of half. Is it? Does anyone for half, right? Okay. So now what this is some Hamiltonian of some spin system, right? But it's also finally it's a matrix, right? It's a matrix in some what dimensional space? It's a matrix of size what? I mean this is this Hamiltonian. 2 to the power, right? Yeah. So if I have I equal to 1 to L. So it's 2 to the power L cross 2 to the power L spins, okay. So now the other thing is in this model is that total spin is conserved, okay. So if you write sum over sigma I z, this you can say commutes with this Hamiltonian, so that this is a conserved quantity, right. So now because of this conservation law, if you look at the structure of the Hamiltonian, it will break up into blocks, right. So whenever you have some conservation laws, means for each conserved value of this, you will get a block. Okay, so this 2 to the power L cross 2 to the power L Hamiltonian breaks up into block where each block is specified by the number of spins, up spins, right? Okay, so now, so if you choose a supposing you choose a sector where there are n up spins. Okay, so then in that sector there are how many states? There are LC n states, right? Supposing you choose a sector where there are n up spins. Okay, then in that sector there are LC n states because you can you have up and down space. You can scramble them in so many ways. So actually, this you can think of these ups like ones and these downs are like zeros, right? So there's a mapping between these two things. Okay, so now if you supposing in this sector. So in this particular sector where there are just n up spins, I look at the structure of the Hamiltonian, right? So now what does this Hamiltonian do? Okay, so what it does is this is a diagonal term. Okay, so it doesn't do much. I mean, it just gives some value of the on the diagonals. But what this does is just if there is a nearest neighbor spin like up and down, it just flips it, right? So it basically takes up to down and down to up. Right, that's what this sigma I plus means. It takes down to up, and sigma I plus 1 minus means it takes the next nearest neighbor, the nearest neighbor to just change sign. So basically, what I'm saying is sigma I plus 1 minus acting on some state like down up takes it to up down. So it's like it's basically like moving a particle from one side to the other, right? So if you look at the structure of this matrix out here, it has actually exactly the same structure as this W matrix out here. Okay, so so for that reason, if you can solve this matrix, I mean, if you can diagonalize this matrix, the Heisenberg matrix, then you can also solve this other problem. Okay, and many of you probably know that this was. I mean, what was the what is the solution of this? How do you solve this? the Heisenberg spin chain. Huh? 1D. No, I mean, so the exact solution is basically by Bethe Ansaj. Okay, so it was first solved by Bethe in no long ago, 1930 or something. So that's the Bethe Ansaj solution of this Heisenberg chain. And then, of course, then we can. So even in the asymmetric case, then you can write some non-Hermitian Hamiltonian, and again you can solve it by Bethe Ansaj. Okay, so that's why the Bethe Ansaj is also useful in trying to understand this. This sort of stochastic processes where again you get a similar matrix. Okay, so this of course you will do in the next class. So I just wanted to give you some feeling so that you already know what to expect next week. Sorry? Two balls can't sit on top of each other. So that is like here also, see, basically any configuration if you think of the spin system. Right, I mean you have 1, 0, 0, 1, 0, 1. And then this corresponds to up, down, down, up, down, up. Yeah, no, so what was your question? Yeah, if it's up anyway, I mean, there's no, yeah. Okay, so this solution of the full, this thing is difficult, but so the next thing that one often does is not to look at the full probability distribution, but to look at moments, right? That is kind of simpler. So let's just see how to, so instead of writing this full liquid equation, which is basically this, right? I mean, you just write down this without, but it's, if you write the equations for the moments, that is kind of simpler. So let's just do that and then we'll stop. Okay, so moments means what? So we have this full so configure. I mean, in phase. I mean, in this configuration space, we have the distribution, which for each for n1, n2, nl. So for each configuration, we have some probability, right? And then we can define, and this whole probability distribution is evolving in time in some way. Okay, so now we can write moments. So for example, if I just want to look at a given site, what is the average number of particles, right? And how does it evolve with time? So I can define Ni average. So this is basically, I have to sum over all configurations. Ni times P of N. And similarly, I can define Nij, which is sum of Ni Nj for all configurations. Okay, so so now how do I write an equation for this dni dt? Okay, so this I'll call as rho I, and this I'll call as Cij. Okay, so now if I look at d dt, so how can this, if there's some number density at some place, how can it change? Okay, so okay, so let's say this is ith site, some site n. So this is, so right now n at this site is 1, right? So it can change in what ways? So it can change if this guy goes to this. Okay, so it can lose and it can go like this, and it can gain if there was a 1 here, and if it was 0 here, then it could have. Okay, so let me just write. Okay, so these are the only two processes by which Ni can decrease at any time, right? That I guess is clear. If it is 1 at some site and either the right side or the left side is 0, then it could have moved and it could have changed, right? So now I want to find what's the probability of this thing. Okay, so what I'll do is I'll write, supposing I write Ni, if I write something like this times this, then this object is non-zero only if this is 1 and this is 0, right? So only if this is satisfied, this is non-zero, right? And in this case, there's a probability that this will increase because this can just go to here. Okay, so this and this will be what? So this will be Ni 1 minus Ni minus 1, and Ni can increase if Ni is 0 and Ni plus 1 is 1 or Ni minus 1 is 1, right? And this corresponds to 1 minus Ni and Ni plus 1, and this corresponds to 1 minus Ni minus 1. See, this product is non-zero only if this is satisfied. Right? That's the only case when it's non-zero. Okay, so now we can just write down this immediately if, once we identify these four processes which can lead to this quantity increasing. Right, so what is this? So this is then basically, so these are the decreased terms. So this means if it's going to this side, so it's R1. Okay, so is this R1 or minus, right? Because these are loss terms. So these are minus and minus. And the gain terms are plus. So from there it's R1. Okay, so this is what you get, and this you can rewrite as if you simplify this and use these definitions rho I and Cij, then this is what you will get. Okay, so now one thing you see, okay, so you can see immediately there's a problem because this is not a closed set of equations, right? So the 1-point functions get connected to 2-point functions, okay? And similarly now if you write something for Cij, you'll find that it gets connected to 3-point correlations, okay, and so on. So therefore, in general, again, this is difficult to solve, but you can make some approximations and which are sometimes very good. So you can solve. So one case which is actually you can solve is if R1 equal to R2. Okay, so that's a symmetric exclusion process. Okay, so for symmetric exclusion process, R1 equal to R2, then these two terms vanish. Okay, so even if though it's an interacting system, the correlation function, I mean the equations for the correlation functions are closed at each order. Okay, so which is good because I mean this equation is just a linear equation in rho, and you already know the solution from the single particle case. Okay, so there's actually not much difference between the single particle case and this interacting symmetric interacting particle case. Okay, but once you have this, then things become more complicated. Right, yeah, so actually, oh yeah, that's, Okay, so even though, okay, so we can't solve this equation, and okay, so one thing that's kind of good about this process is that, okay, so I can write some W matrix, and this is the rate equation. So one thing you can show is that both for the symmetric and asymmetric exclusion process, the steady state is actually very simple. Okay, so the steady state is basically all states are equally probable. Okay, I mean all configurations equally probable. Okay, and that is so what you can do is the way to show it is in the case of symmetric exclusion it's simpler. So what you show is you take any configuration and you see so supposing you assume that all configurations are equally probable. Okay, so then for any configuration you see there's another configuration. Okay, so let's give an example. So let's say 1 0 1 1 0 1 0 1. And so then let's look at another configuration which is 1 0 0 1 1 0. Okay, so just these two guys are interchanged, right? So for any configuration you can find another configuration which differs by just an exchange. Okay, and if we say that all states are equally probable, then the detailed balance condition is obviously satisfied. Okay, so the probability of transition from this to this, so I'm saying let's say the equilibrium, the steady state is all states equally probable. Okay, and then you can see that the transition rate from here to here is the same as from here to here. So therefore for this pair of states and for any two states you can construct pairs such that this detailed balance condition is satisfied. Okay, so therefore this steady state with all states equally likely is the steady state. Is that clear? So actually you can also find all in the steady state, you can, since you know the steady states, you can find all steady state correlations and so on, but those are not time dependent, right? Those are time independent correlations. If you want to find time dependent correlations, then it's then you have to make various assumptions and so on, and which I won't go into.